in this video, we'll take a look at simple and multiple linear regression estimates and see that there is some sort of a bias that might appear in simple linear regression estimates if we have an omitted variable. So we'll begin with just saying that the simple linear regression estimates are going to be denoted by tilde. So you're going to see the tilde on beta naught and beta 1. And for the multiple linear regression case, you're going to see the hats, okay? So you're going to have beta naught hat, beta 1 hat, and beta 2 hat that we're estimating. Okay, so tilde for the simple linear regression and hat for the multiple linear regression case. Now, one question we might want to ask ourselves is that, is there a simple relationship between the slope coefficient from the simple linear regression case and the slope coefficient from the multiple linear regression case? Okay, and so what we can do is actually try to estimate the relationship between the missing variable x2, which we're trying to introduce in a multiple linear regression case, and x1, which goes into both the regressions. Okay, so it's always going to be true that such a relationship will hold. So here we're basically saying that the slope coefficient from our simple linear regression case, this is the slope coefficient from the simple linear regression case, equals the slope coefficient from the multiple linear regression case plus some sort of a bias, right? And this bias is the product of beta 2 hat, which is coming from the multiple linear regression, and this regression of x2 on x1. Okay, so this guy right here. And here we can put tildes to signify that these are, or to denote that this is an estimated regression. So we can put a tilde here. Okay. Okay, so now if we want to understand what is the, what would happen if we compared beta 1 tilde to beta 1 hat, we might want to try to look into what is going on with this product right here. And what is the sign of that, and what is the magnitude? Okay, so let's take a look at case 1. The first case says that if both beta 2 hat and delta 1 hat are positive, then it is going to be true that beta 1 tilde is going to be greater than beta 1 hat. So you're going to have some sort of a positive bias or an upward bias in the simple linear regression estimate or coefficient, okay? And this would also hold true if both of this product, right, as long as this product is positive, right? So you could have both of these to be negative and then the product is positive. Similarly, we could have, so here is an example before we move on. So we saw that when we only regressed log wage on education, the return was 9.9%, but it dropped to 7.3% when we introduced IQ as another variable, right? So this was a simple linear regression case, this was the multiple linear regression case, and the returns to education dropped to 7.3%. So again, this was our beta 1 tilde and this was our beta 1 hat. So this happened because the correlation between education and IQ was positive, okay? And also beta 1 hat was positive, okay? So because these two were positive, the bias is positive, and therefore you have beta 1 tilde greater than beta 1 hat. Now we can consider another case where the signs are opposite. So let's say beta 2 hat is greater than 0 and delta 1 hat is negative. So we saw that in the example with the attendance data, where we were trying to predict final exam score using data on missed lectures and prior GPA. Right? So this is our simple linear regression case. This is our multiple linear regression case. And we said that the correlation between missed lectures and prior GPA is actually negative. But the coefficient on the missed lectures in the multiple linear regression case, which is to say that beta hat missed is greater than 0, right? So we had these two, and this makes the product negative, and therefore you had beta 1 tilde less than beta 1 hat, which is your coefficient on missed lectures, okay? So beta 1 tilde was negative and beta 1 hat was positive, right? So that relationship holds. Now, another thing you might want to consider when you're thinking about multiple linear regression is that sometimes you might be curious, well, what happens if we impose that the predicted y is 0 when all of the x's are 0, right? So we're basically saying that this is the zero intercept assumption, or we're trying to impose that the intercepts should be 0, okay? So this is the case of regression through the origin. And so you can think about a regression in which there is no intercept, which is what is depicted here. Okay, now the problem with such a regression is there is a cost to it, okay? That all of the slope coefficients that you estimate are going to be biased in general. And this is a severe cost.